Welcome to the Deep Dive. Today, we're going to dive into a topic that's, well, it's both a scientific puzzle and potentially a key to a greener future.
Yeah.
Hydrogen storage and transportation.
It's a big one.
It is a big one.
Yeah.
We've got a stack of research here, and we're going to break it down for you, starting with the fundamental science and then exploring the real-world challenges and innovations.
That's the fun part.
That is the fun part.
Yeah. It's fascinating, isn't it?
It is.
Hydrogen is the most abundant element in the universe, and yet harnessing its energy is surprisingly tricky.
Yeah.
It all comes down to the unique properties of this tiny energetic atom.
Okay, so before we jump into the specifics of storage and transport, let's talk about why hydrogen is such a challenge to wrangle.
Exactly. Let's start with the most basic issue. Hydrogen's incredibly low density. It's the lightest element, meaning it takes up a lot of space for a given amount of energy.
Yeah.
Imagine trying to fill a swimming pool with balloons.
Yep.
It's going to take a lot of balloons to get any real volume.
So even if we could perfectly contain hydrogen, we need enormous tanks just to store a usable amount.
That's one of the major hurdles. And then there's the fact that hydrogen is highly reactive.
Yeah.
It loves to combine with other elements, which can be great for things like fuel cells, but it also poses safety concerns. We need to make sure it doesn't react with its container or anything else it comes into contact with.
It sounds like we're dealing with a tiny, energetic firecracker that needs a very specific and secure container.
Precisely. And to make matters even more challenging,
oh boy,
hydrogen molecules are incredibly small. They can easily diffuse through even the tiniest openings.
Right.
Think of trying to hold water in a sieve.
Okay.
Hydrogen is that slippery.
Okay.
This makes preventing leaks a constant concern.
So low density, high reactivity, and a master escape artist.
Right.
No wonder hydrogen storage and transportation are such hot topics in the energy sector.
Indeed. But it's these very challenges that make the research so exciting.
I bet.
Scientists and engineers are coming up with some ingenious solutions, and those solutions fall into two broad categories: physical storage and material-based storage.
Let's start with physical storage.
Okay.
I imagine this involves physically manipulating hydrogen to make it more manageable.
You got it. One common approach is compressed gaseous hydrogen, or CGH2.
Okay.
It's exactly what it sounds like. Squeezing hydrogen gas into tanks under high pressure.
What kind of pressures are we talking about here?
Typically, pressures range from 350 to 700 bar, which is about 5,000 to 10,000 pounds per square inch.
Okay.
So significantly more pressure than, say, a car tire.
Right.
This high pressure forces the hydrogen molecules closer together, increasing its density.
That makes sense, but those must be some seriously robust tanks.
Absolutely. The tanks need to be incredibly strong and durable to withstand these pressures. They're typically made from composite materials like carbon fiber, which are lightweight, yet incredibly strong.
So high pressure tanks are one way to go. Are there any other physical storage methods?
Another approach is to cool hydrogen down to extremely low temperatures, turning it into a liquid.
Okay.
This is known as liquid hydrogen, or LH2. Liquid hydrogen is much denser than compressed gas, allowing you to store more in the same volume.
How cold does it have to get to turn hydrogen into a liquid?
We're talking extremely cold, around negative 253 degrees Celsius or negative 423 degrees Fahrenheit.
Wow.
To put that in perspective, that's colder than the surface of Pluto.
Wow, that's incredibly cold. Maintaining those temperatures must be a challenge.
It definitely is. Liquid hydrogen requires sophisticated insulation and specialized storage tanks to minimize boil-off, which is the evaporation of some of the liquid, due to heat leakage.
So there's a trade-off between storage density and the energy needed to maintain those cryogenic temperatures.
Right.
Is there a way to kind of strike a balance between compressed gas and liquid hydrogen?
There is. It's called cryo-compressed hydrogen, or CCH2.
Okay.
This method combines high pressure and low temperature, not quite as cold as LH2, to achieve even higher densities than either method alone.
So it's like a hybrid approach.
Yeah.
What are the advantages of using cryo-compressed hydrogen?
Well, it allows for higher storage density, but perhaps more importantly, it reduces the boil-off issue associated with liquid hydrogen.
Okay.
By operating at a slightly higher temperature, you minimize the amount of hydrogen that's lost to evaporation.
So cryo-compressed hydrogen offers some compelling benefits, but it sounds like a more complex system to manage.
That's true. It requires careful control of both pressure and temperature, and the technology is still under development.
Yeah.
However, it holds a lot of promise for the future of hydrogen storage.
It sounds like physical storage methods offer a range of options, each with its own set of advantages and challenges.
Yeah.
But we also mentioned material-based storage.
Right.
What's the basic idea behind that?
Material-based storage involves using materials that can chemically or physically bind hydrogen, allowing us to store it at much higher densities without the need for extremely high pressures or extremely low temperatures. It's like trapping the hydrogen within the material itself. One example is metal hydrides, which are metals that can absorb hydrogen atoms into their structure, almost like a sponge absorbing water.
So the metal acts like a hydrogen container, but on a microscopic level.
Yeah.
That's pretty neat. Are there any other materials that can do this?
There are. Complex hydrides, which are compounds containing hydrogen, offer another approach. These materials can release hydrogen under specific conditions, making them promising candidates for controlled release systems.
So it's like having a hydrogen reservoir that you can tap into on demand.
Exactly. And then there's another intriguing category called liquid organic hydrogen carriers, or LOHCs. These are organic liquids that can be chemically loaded and unloaded with hydrogen.
So instead of storing hydrogen directly, we're using these LOHCs as a sort of hydrogen shuttle.
Precisely. Think of it like a tanker truck transporting gasoline. But instead of gasoline, it's carrying hydrogen bound within the LOHC molecules. This approach offers some potential safety advantages, because LOHCs are typically less flammable and less prone to leaks than hydrogen gas itself.
That's fascinating. It seems like material-based storage opens up a whole new world of possibilities for hydrogen storage.
It does.
But are these technologies ready for prime time?
Well, that's where things get really interesting. Many of these material-based storage technologies are still in the research and development phase. They hold immense potential, but also face challenges related to cost, efficiency, and durability.
So what are some of the key hurdles that researchers are working to overcome?
One challenge is finding materials that can absorb and release hydrogen quickly and efficiently under practical conditions. Another challenge is improving the durability of these materials. They need to be able to withstand repeated cycles of hydrogen absorption and release without degrading.
It sounds like there's a lot of exciting research happening in the field of material-based storage.
There is,
It'll be interesting to see how these technologies evolve in the coming years.
Absolutely. Now that we've explored the various ways to store hydrogen, let's shift gears and talk about how we actually move this fuel of the future around the world of hydrogen transportation.
It seems like transporting hydrogen would come with its own set of challenges.
It does,
given its unique properties. Where do we even begin?
Well, just like with storage, we have a range of options, each with its pros and cons.
Okay.
For shorter distances and smaller quantities, compressed gaseous hydrogen trailers are a common choice.
So we're talking about those big tanker trucks we see on the highway.
Exactly. These trailers are specifically designed to carry high-pressure tanks.
Right.
Filled with hydrogen gas. But remember, hydrogen's low density means that even under high pressure, a CGH2 trailer carries significantly less energy compared to a gasoline or diesel tanker.
So it takes more trips to transport the same amount of energy.
Right.
What about transporting larger quantities over longer distances?
For those situations, liquid hydrogen tankers come into play.
Okay.
These are specialized, heavily insulated trucks designed to transport hydrogen in its liquid state at those extremely low temperatures we talked about earlier.
I imagine it's like a super high-tech version of a milk truck, keeping the hydrogen chilled throughout the journey.
Yeah.
But what about transporting hydrogen across oceans or to different countries?
That's where things get even more interesting. For long-distance international transport, we need to think outside the box. Shipping liquid hydrogen is one possibility. But those boil-off losses we discussed earlier become a major concern over long journeys.
So how do we prevent the hydrogen from simply evaporating away during transport?
One solution is to use those liquid organic hydrogen carriers, those LOHCs that we talked about earlier. Remember, they can be chemically loaded and unloaded with hydrogen, making them a potentially safer and more efficient way to ship hydrogen across oceans.
So it's like sending the hydrogen on a stealth mission disguised as a regular liquid cargo.
Right.
That's pretty ingenious.
It is. And because LOHCs are typically less flammable and less prone to leaks than hydrogen gas,
Right.
they offer some inherent safety advantages during transport.
It sounds like LOHCs could be a game changer for international hydrogen shipping.
They certainly have the potential. Of course, the technology is still under development, and there are challenges related to scaling up production and optimizing the loading and unloading processes.
Right.
But LOHCs represent a promising avenue for long-distance hydrogen transport.
So we've got trucks, we've got ships. Are there any other ways to move hydrogen around? What about pipelines? I know they're used for natural gas. Could we use them for hydrogen as well?
That's a great question. Pipelines are definitely another option for transporting large amounts of hydrogen over long distances.
Right.
We can either repurpose existing natural gas pipelines or build new ones specifically designed for hydrogen.
Repurposing existing infrastructure sounds like a cost-effective solution.
It can be.
Are there any challenges with that approach?
There are a few things to consider. Natural gas pipelines are typically made of steel,
Okay.
which can be susceptible to hydrogen embrittlement.
Hydrogen embrittlement, what exactly is that?
It's a phenomenon where hydrogen atoms can penetrate the steel's structure, making it brittle and more prone to cracking. This is a serious concern for pipeline integrity and safety.
So using existing pipelines for hydrogen requires careful assessment and potential modifications to mitigate the risk of embrittlement.
Exactly. There are various techniques to address this, such as using coatings or liners inside the pipes, or even replacing sections with more hydrogen-resistant materials, but it adds complexity and cost to the equation.
What about building new pipelines? Specifically for hydrogen, wouldn't that circumvent the embrittlement issue?
It would, and it allows us to use materials that are inherently more resistant to hydrogen embrittlement, such as specialized polymers or composites. However, building new pipelines is a significant investment, requiring careful planning and coordination, not to mention navigating the permitting and regulatory processes.
It sounds like there's no easy answer when it comes to hydrogen transportation.
Right.
Each method has its own set of advantages and challenges.
Yeah.
But it's exciting to see the range of options being explored, from trucks and ships to pipelines, and even some more unconventional ideas.
It is. And the innovation doesn't stop there. Researchers are exploring some truly outside-the-box concepts. For example, some are investigating the use of ammonia as a hydrogen carrier.
Ammonia. Isn't that a pretty harsh chemical? What makes it suitable for hydrogen transport?
While it's true that ammonia requires careful handling, it has a surprisingly high hydrogen content.
Okay.
And importantly, we already have existing infrastructure for transporting and storing ammonia.
Right.
The idea is to transport the ammonia and then extract the hydrogen at the destination.
So it's like a hydrogen delivery service, using ammonia as the vehicle.
Yeah.
That's fascinating. Are there any other unconventional methods being explored?
Believe it or not, some researchers are even exploring the use of airships or Zeppelins for hydrogen transport.
Zeppelins. Now that's thinking outside the box.
Right.
But seriously, are Zeppelins a practical option for hydrogen transportation?
It's certainly an intriguing concept, especially given that hydrogen is lighter than air.
Right.
However, there are significant challenges related to cost, scalability, and safety regulations. But as technology advances and the demand for hydrogen increases, we might see some of these unconventional methods become more viable.
It's amazing to see the ingenuity and effort going into making hydrogen a practical fuel source.
It is.
We've talked about storing it in everything from high-pressure tanks to metal hydrides and transporting it in everything from trucks to Zeppelins. It seems like every aspect of the hydrogen energy system is brimming with innovation.
It really is. But it's important to remember that the story doesn't end there.
Okay.
Those material-based storage methods we discussed earlier play a crucial role not only in onboard storage for vehicles, but also in large-scale stationary storage.
Okay.
This is essential for creating a robust and resilient hydrogen infrastructure.
Stationary storage, what exactly do you mean by that?
Imagine massive underground storage facilities filled with metal hydrides or other hydrogen-absorbing materials.
Okay.
These facilities could act as giant hydrogen reservoirs, allowing us to store vast quantities of hydrogen produced from renewable energy sources, like wind and solar power.
So instead of just transporting hydrogen, we're talking about storing it on a massive scale.
Yeah.
Almost like we have natural gas storage facilities today.
Exactly. This large-scale storage is crucial for balancing supply and demand,
Right.
especially when we're dealing with intermittent renewable energy sources, like solar and wind power.
That makes a lot of sense. We could store excess hydrogen produced during times of peak generation and then release it when demand is high or when renewable energy production is low.
Precisely. These storage facilities would act like giant energy buffers, helping to smooth out the variability of renewable energy and ensure a reliable supply of hydrogen.
So material-based storage technologies are key players in both the transportation and stationary storage aspects of a hydrogen-based energy system.
They are.
It's all interconnected.
It is. And it highlights the importance of a holistic approach to developing a hydrogen infrastructure.
Right.
Advancements in material science, storage techniques, and transportation methods all contribute to making hydrogen a more viable and sustainable energy carrier.
It's fascinating to see how all these different technologies are intertwined and how they could potentially revolutionize the way we produce, store, and use energy.
Absolutely. And it's not just about the science and engineering.
Right.
There are also economic and environmental considerations that play a crucial role in making hydrogen a truly viable alternative to fossil fuels.
Right. Because at the end of the day, it all comes down to practicality. No matter how ingenious the technology is.
Right.
It needs to make sense economically and environmentally.
Exactly. One of the key factors is cost.
Yeah.
Currently, producing, storing, and transporting hydrogen is still relatively expensive compared to conventional fossil fuels.
Right.
Bridging that cost gap is a major focus of research and development.
So what are some of the strategies for bringing down the cost of hydrogen?
There are several approaches.
Okay.
One is to improve the efficiency of hydrogen production methods. Electrolysis, which uses electricity to split water into hydrogen and oxygen, is a promising pathway, especially if we can power it with renewable energy sources, like solar and wind.
So making green hydrogen more cost competitive is essential. What about the cost of storage and transportation?
Advancements in those areas are also crucial. For example, improving the performance and durability of those material-based storage technologies like metal hydrides could significantly reduce storage costs.
And finding ways to minimize boil-off during liquid hydrogen transport would also help reduce costs and improve overall efficiency.
Absolutely. But cost is only part of the equation.
Right.
We also need to consider the environmental sustainability of the entire hydrogen life cycle from production to end use.
Right, because the whole point of exploring hydrogen is to transition to a cleaner and more sustainable energy system.
Exactly. And that means ensuring that every step of the hydrogen journey has a minimal environmental impact.
So if we're producing hydrogen from fossil fuels without capturing the carbon emissions, that kind of defeats the purpose, doesn't it?
It does.
Yeah.
That's why there's a strong emphasis on green hydrogen, which is produced using renewable energy sources like solar and wind.
Right.
By decarbonizing the hydrogen production process, we can ensure that the entire hydrogen supply chain is truly sustainable.
Green hydrogen sounds like the way to go, both economically and environmentally.
It does.
But are there other environmental factors to consider beyond just the production phase?
There are. For instance, even the transportation of hydrogen, especially in its liquid form, requires energy for cooling and can result in some greenhouse gas emissions.
Okay.
We need to keep optimizing those transportation methods to minimize those emissions.
It seems like there's always this balancing act between efficiency, cost, and environmental impact.
That's true. And we also need to consider the potential environmental impacts of those large-scale hydrogen storage facilities.
Right.
Just like with any major infrastructure project, we need to ensure that their development and operation are done in an environmentally responsible manner.
It's a complex puzzle with many pieces to consider, but it's encouraging to see so much progress being made on all these fronts.
It is, and it's important to remember that hydrogen is not a silver bullet solution.
Right.
It's one piece of a larger puzzle in our transition to a more sustainable energy future.
Right, because we need a diverse mix of energy sources and technologies to meet the world's growing energy demands in a way that's both sustainable and reliable.
Exactly. That's where the concept of an energy mix comes in.
Okay.
We'll need a combination of renewable energy sources like solar, wind, and hydro, along with potentially nuclear power and, yes, even hydrogen, to create a resilient and sustainable energy system that can meet our needs for generations to come.
So hydrogen has the potential to play a significant role in our energy future, but it's not about replacing everything else. It's about finding the right balance and using each energy source where it makes the most sense. considering both its strengths and its limitations.
Well said. It's a fascinating and constantly evolving landscape, and it's exciting to be a part of this conversation.
It truly is. Well, that brings us to the end of our deep dive into the world of hydrogen storage and transportation. We've explored the fundamental science, the challenges, the innovations, and the broader implications of this potential fuel of the future. It's been a journey from the incredibly small, the tiny hydrogen atom, to the incredibly large, massive underground storage facilities. We've covered a lot of ground, spears, but this is just the beginning. The field of hydrogen energy is constantly evolving, and there's always more to explore. We encourage you to continue your own deep dive into this fascinating topic, to stay curious, and to engage in the conversation about how we can create a brighter and more sustainable energy future for all.
Remember, knowledge is power. Smits. And the more we understand about these transformative technologies, the better equipped we are to make informed decisions and contribute to a future powered by clean, sustainable energy. Until next time, keep exploring.